Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're back again for week 5 of this course called Fundamentals of Atomic Force Microscopy. This is part 1 of the course, and this will be the final week of lectures for part 1. In week 5, we're going to focus largely on performing numerical simulations of many of the ideas that we've already discussed in the first 4 weeks of the semester. And to do that, we're going to rely heavily on this software called VEDA. We've already talked about VEDA in week 3, and specifically the second lecture in week 3. So by now you should have it, you should be able to get ready access to it on your computer. If you have not yet installed, or if you have not yet accessed VEDA, I'll just remind you that you're going to need to download the Java program 1.4 or higher. There's a direct link from the VEDA web page to the Java website, which will allow you to download that software at no cost. So that has to be installed before you actually try to use the VEDA simulation. By way of an overview for week 5, I'd like to pull up this bubble diagram and try to emphasize to you that we're going to cover a fair number of topics, but the topics are now going to be covered using the VEDA simulation. So rather than discuss the theory or the practice behind each of these subjects, we'll now simulate these quantities in VEDA. So let's get down and start to do a few of these simulations and walk you through them. First, I'd like to make just a few comments, right? Just general ideas that have occurred to me over the course of this 5 weeks of lectures. Probably it's more effective use of your time to learn how to use VEDA than to try to write all the software that VEDA already has loaded into it. So in this way, you'll be able to improve your efficiency in performing experiments because you'll have a much better idea of what to expect from an experiment before you actually take the experimental data. There are a few cautionary notes that I should say up front. If you see an empty graph after a simulation using VEDA, you can go to the results menu, right? And in the Simulate tab, select the message called Error Message, and click on that, and usually you'll get a helpful hint that explains to you why your simulation produced a null result. Some of the inputs to VEDA often require 2 values. When you enter in those 2 values, you have to make sure that the 2 values are comma separated. If they're not, you're going to run into trouble. This probably doesn't apply too much for the simulations we're going to run, but if you start to do dynamic AFM simulations, this becomes an issue, but I just mentioned it up front. Sometimes you'll get a plot and it doesn't make sense to you, right? What do? My advice is to change the value of the spring constant of the cantilever. Most of the simulations that we're going to perform depend on the spring constant in a very direct way. And so by changing the spring constant, you should be able to make some headway into sorting out what the plots actually are trying to tell you. Very often when you use VEDA for the first time, there's a wide variety of input parameters that you have to specify. My advice is the first time you use a particular application, just use the default parameters that are given in VEDA. These default parameters have been chosen to give you a reasonable plot. So rather than starting to tailor the input parameters to your particular application, make sure that you understand the plot that you get with the default parameters. And then the other issue I'll mention is that sometimes when you run a simulation, it will time out before it even begins. When this happens, this usually is telling you that your feedback parameters for your feedback loop in the software are probably set too high. So you probably need to reduce those values for the proportional and integral gain until your simulation works in a reasonable amount of time. So if you get a timeout, please pay attention to the feedback parameters. That's most likely the problem that you're going to encounter. The other issue is the input parameters that you are required to initialize. I think we've pretty much explained all those input parameters in the first 4 weeks of the lecture. So if you've understood what we've discussed in the first 4 weeks of the lecture, inputting those parameters should not be a terrible mystery to you. If you have any questions about what the simulation is trying to do, there's a very nice VEDA manual which is available to you from the VEDA website. I list the URL here for you to access that manual. If you have any type of reliable internet service, I will tell you that probably the longest time you're going to wait for a simulation to be complete in this week of the lectures is about a minute or so. If you're waiting much longer than a minute or so, something's probably wrong. But certainly all the simulations that I'm going to run through have typically completed in less than a minute. And then the other thing I'll mention is whether you're approaching the tip to the substrate or withdrawing the tip from the substrate, that can be controlled by simply specifying the initial and final Z separations. So for instance, if your initial Z separation is plus 6 nanometers, if your final Z separation is minus 6 nanometers, then that indicates an approach curve. If you reverse the initial and final separations, so you make the initial separation negative, the final separation positive, that's a withdrawal. So you can do both an approach and a withdraw simply by doing 2 separate simulations and just changing the Z initial and Z final variables. For the first simulation that we're going to do today, I like to walk through a force distance simulation using VEDA. There's a variety of ways to access the VEDA software. One is to go to the nanoHUB. The other is to go to the course page on nanoHUB-U. Both those routes should allow you to readily access VEDA. And the other thing I'll say is it's not clear how to step through these simulations. There's an issue about whether we want to try to do them in real time or whether we want to capture the important results using screen capture. I've sort of settled on the second approach, and I've annotated the screen capture with some numbers, numbered bullets that describe important features. I've also used red circles to indicate input values that you have to select and you should maybe be focusing on when you try to do these simulations. My advice is probably to print out the slide lectures and have them in front of you when you do the simulations, because that way you can refer to the screen capture to make sure that what you're entering into the computer is exactly the same as the parameters that I entered in. So let's do the first application. It's a force distance curve. What you have to do is you have to go to the application window and select force distance curve as indicated by the red circle in this slide. You then have to select the contact model that you want to simulate. So there are a variety of different contact models. We discussed the Hertz, the JKR, and the DMT models earlier on in these lectures. For this particular application, I selected the DMT model. When you select the DMT model, VEDA gives you a schematic plot of the interaction force that you're going to use when you simulate let's say the force versus Z, force versus displacement experiment. If you select the default values that come up when you use the DMT model, and you press the simulate button, in a few seconds you should see a plot that looks somewhat similar to the one that I've shown here. Once you do this simulation, VEDA calculates a wide variety of different outputs that are of interest. These different outputs are sort of indicated by the words in the red box here. You're free to select whichever output you want in order to try to understand what the simulation is trying to tell you. Very often you don't get the initial and the final values of Z correct the first time round, so you shouldn't worry about that. You should just take advantage of the zoom in feature. So for instance, you can drag and draw a box around the feature of interest, and when you double click, that region of the graph will expand and allow you to see in more detail exactly what's going on. So I did that here. This is experimentally what you should see. This is the observed deflection of the cantilever. This is the parameter Q in all previous lectures versus the displacement of the Z piezo in nanometers. What you can see from this plot is you can see very clearly that there's an interaction force that's attractive as the tip approaches the substrate. This interaction force is the one that we discussed in week 2 of the lecture. You can see the cantilever snap into the substrate. You can see what appears to be noise after that snap-in. I believe that noise is actually due to an oscillation of the cantilever as it comes into contact with the substrate. The software simulates that all those dynamics accurately. And then as you continue to approach the substrate to the tip, you can see that the cantilever is loaded against the substrate, and there's this very linear regime in which the tip is displaced in proportion to the substrate to the Z displacement, to changes in the Z displacement. With this ability to do simulations, you can start to do examples, and you can start to get build up some confidence in the types of force versus distance curves you might see in experiment. So I just cook up a simple example here. I have 2 samples, A and B. One sample has a Young's modulus of 1 gigapascal. The other has a sample of 1/10 of a gigapascal. What we're asking you to do is perform a FZ simulation, starting at +5 nanometers, going to -5 nanometers. We'd like you to compare the force versus distance data that you get to an infinitely hard sample, and then also try to answer the question, what is the indentation of the tip into the sample that you would expect if the sample has a Young's modulus of 1 gigapascal or 1/10 of a gigapascal. So except for the substrate's Young's modulus E, it's probably easiest to just use all the default values provided by VEDA. And in this particular example, we're going to use the DMT tip sample interaction potential. Just to be clear, I give a list of the echo input file that was generated when I did this simulation. This echo input file has a large number of parameters. Many of the parameters are not associated with the specific simulation that you're trying to perform, but I've circled a few here just to show you that you can cross-check and make sure that VEDA is in fact using the parameters that you input at the various steps along the way for this simulation. So in this particular case, I selected a spring constant of 5 newtons per meter. I think that's a default. The tip radius is 10 nanometers. That's also a default. The tip modulus is 130 gigapascals. That's also a default. Those numbers can clearly be changed, but for the purposes of this simulation, these are the values that we've selected. The results of the simulation for the 1 gigapascal and 1/10 of a gigapascal Young's modulus for the sample are displayed here. You can see that the plot ranges from +5 nanometers to -5 nanometers, so this is an approach curve. I've selected the all button to display both simulations on a graph, and then I've labeled each simulation with the Young's modulus for the substrate, 1 gigapascal and 1/10 of a gigapascal, just so it's clear which simulation is which. So this is a plot of the deflection of the cantilever Q versus the sample displacement Z. You can again clearly see the van der Waals forces interacting between the tip and the substrate before contact, and then after contact you can see what the predictions of the DMT model might be for these two particular substrates. So in this way, if you have deflection versus Z data, and the deflection data has been carefully calibrated into nanometers, the Z displacement usually is in Z nanometers automatically. If you have that type of data, you can try to fit it and infer what, let's say, the modulus of the sample is in this particular case. You can also get an estimate of what the Hamacher constant is that's describing the interaction between the tip and the substrate before you jump to contact. If you magnify the jump to contact region, that's what I've done here. In this particular case, I'm again plotting the deflection of the cantilever versus the Z displacement. And this time around, I've added a curve for an infinitely hard substrate. The infinitely hard substrate I approximate as a Young's modulus of 500 gigapascals. You can see the slope of the Q versus Z curve now is 1 for that particular sample because there's no indentation. As you displace the sample towards the substrate, the tip deflection Q is just going to mirror Z, and you get a slope of 1 for that particular simulation. For the simulations of softer substrates, you can see that there's a distinct deformation, and you can, in principle, you can read that deformation off from this plot by referencing the red fiducial marks that I've added to the plot. So the wording on this particular simulation is something that I've added after the fact. Hopefully it makes it a little bit simpler for you to understand the plots. I'll just mention that you don't have to measure the deformation from these plots. By selecting the indentation result, you can get a direct plot of indentation versus Z, and I've done that in this particular example. Here I plot how far the tip is indented into the substrate, both for the 1/10 of a gigapascal and a 1 gigapascal substrate. And this is plotted as a function of Z. So this is an output that you would have to analyze your experimental data in order to compare, but VEDA gives you this output in a very simple and straightforward way. Lastly, it's useful to plot the tip sample gap. versus the Z displacement. Of course, the tip sample gap is the fundamental parameter. That's what all the theory about tip sample interaction forces contain. But again, this is very simple to plot out in the simulation. You just go to the results window at the top of the simulation tab, and you just select tip sample gap versus Z distance. When you do that, you'll get a plot that looks like this. I've included the 500 gigapascal substrate modulus as an example. For a 500 gigapascal substrate modulus, the separation D between the tip and the substrate should be pinned at essentially 0. Technically, it should be at A0, which is the separation between the tip and the substrate. But unless that's specified in the simulation, that wouldn't show up on this plot. So instead, what you find is that the tip sample gap is represented by a horizontal line, which is essentially centered at 0, and that represents the tip sample gap as a function of Z for an infinitely hard substrate. If you go to the softer substrates, the VEDA simulation also provides you with information about tip sample gap versus Z displacement. Just mentioned that in the case of the very soft sample, Q is essentially 0 because the cantilever is indenting into the substrate. So if Q is equal to 0, D should be proportional to Z, and that proportionality is indicated by the red line in this plot. So you can see that for soft samples, there's a pretty good proportionality between D and Z. Sort of, I would hope it's obvious why that is, right? That's something that the first 4 weeks of this lecture should allow you to understand. I've also included in the appendix a second example. The second example refers to applying a force no greater than 500 piconewtons to a soft substrate which has a Young's modulus of 0.5 gigapascal. I ask a series of simple questions that you might find interesting experimentally, because if you're trying to do an experiment on a soft sample, you certainly don't want to deform it permanently by indenting it. So this second example just all the screenshots from the simulation are available in the appendix, and we encourage you to look through that when you have some time. So that's all I wanted to say about the simulation of force distance curves. Hopefully this gives you a broad enough overview that you can actually go into VEDA and start to simulate curves that are of interest to you and your research topic. So up next, we're going to do a little bit more force versus distance simulations. We're going to talk a little bit about the JKR model, and we're going to investigate the radius of the tip explicitly, and we'll also have an example on capillary forces involving the Hertz model. So come on back to second lecture of week 5, and we'll discuss some of these simulations in more detail. Thank you very much.